go over a concept that a lot of people are somewhat familiar with. Like you have some sort of idea as to what chaos theory is. And it's kind of like more of a fun area of mathematics to me. It seems to be like an area of mathematics that people have more interest in overall. So to me, it's kind of an interesting topic to discuss and to go over. And so the main point that I want to highlight with this particular video overall, and the main thing to get across is that like a lot of people have this idea of trying to eliminate um, what we see it manifest as like hallucinations, as like probabilistic outcomes, things like that within like AI models overall. And the big thing to me to get across is that we will never be in a world where that is actually going to be the case, where we can actually eliminate any sort of predictability or unpredictability within models. It just won't happen. There won't be a world within it. And because of the simple fact that the AI in that instance won't operate as well as the probabilistic AI. And so in this instance, it gives you kind of a real world example of this, and really straightforward real world example. And so that's why I want to illustrate this and why we're starting here at the bottom of like the outcome of this. And the outcome is, to me, the most important part of this, right? Because it's why are we doing this? And then so I'll explain this algorithm in more detail, but it's kind of an overall interesting algorithm to me. Uh, I call it chaotic simulated annealing. And then it's essentially it's a process of the process of annealing, which is like where metal cools based off of temperatures, and then you can get different reactions based off of that. And then so it's literally like utilizing that as the base concept for the algorithm, but this is with regards towards trying to find essentially like the optimal way to produce results within projects. And I'll show exactly what this is breaking down here at the end, but we can see that it comes up with the best solution very quickly, right? And we can see it in this chart, in this graph. And the chart on the right, the red chart, is the most important chart to look at for me. And then so again, going back to that base question of like, why would we do this? Why are we doing this? And so we can see that what happens when this algorithm first starts is it goes into what we call like a local minima and local maxima, right? Like it's essentially it's going within this certain range up and down, but the graph stays in that range, right? And that continues for about like 150 iterations or so, where it's like stuck in this range. And so if you train AI models, this like where it gets like stuck in that range, very common problem, right? Like that happens all of the time. And then so you see a lot of things within training of AI and within AI overall, like disruption. In this case, I'm putting in chaos theory directly into it. And so the chaos theory or the disruption or whatever technique that you're utilizing is to get the model specifically out of this local minima. Like you don't want this to occur because this isn't the actual uh, ceiling and floor, right? It's just like this is just where it gets stuck because it hits for whatever reason just a local minima in the data, and it'll get stuck there. You need a way to like kickstart it, restart it. And then so you put in a little bit of chaos theory, and then that's what happens, and then it'll kickstart out, and then around see around like right around like 100 iteration 150, it's like, oh, I can actually go down, right? And then right before iteration 200, like after like only like 25 iterations of getting kicked out of that, it's like, okay, boom, I've found the floor, and then it's just like the floor from then on out, like about iteration 175 or so, it doesn't change, right? It's just like, okay, I found the solution. And then so going back up here, I'll explain what this algorithm is and like what that solution is, right? So this is to me kind of a really straightforward algorithm. Up front, I'm using a few libraries. I'm using random, which is where we're getting the chaos theory from, and then math via matplotlib. And then so essentially up front, I'm defining a function to for it to iterate on, and then so this is the mathematical function that I'm giving it here, and then so essentially this mathematical function is essentially just trying to have it find the local minima, like the global minima of the not local, global, of the equation overall, right? Um, and then so then I'm giving it what this is as far as I have the like what tardiness is, and then as well as like what annealing is, like this annealing algorithm, right, and how it should work, and what the annealing process is, which in this instance is is tardiness, right? And then so essentially we want to decrease the amount of tardiness, and then we're mapping that to like a decreasing temperature, like what annealing is, right? like so decreasing temperatures would be a equal to a decrease in tardiness, and then going down like just putting the math behind that, and then so kind of like what tardiness is, that comes in with our example usage of the code here. And then so with this example usage of the code, we've got a few projects, project A, B, C, D, and E. And then each one has different due dates. So project A is 5, B 7, C 3, D 9, E 6, just random due dates, right? And then processing times that are different than the due dates. So process time of 3, 2, 4, 1, and 2. And then so for project A, it's due in 5 days, and it will take you 3 days to complete it. So if you started it today and it's due in 5 days, you would be early, right? Because you'd be waiting 2 days. But if you started 3 days from now, you would be 1 day tardy by doing that. And then so that's kind of how that equation works, right? And then so it's breaking down and trying to solve for this. So then given this specific input and this specific equation, what exactly is the best order of operations for these projects? Like what would be the way that you can complete all of the projects with the least amount of tardiness based off of like the processing time and the due dates. And then so what it finds is that in order to complete all 5 of the projects, we're going to be about 9 days tardy overall across all 5 projects. And then the best way and the best order to complete complete those projects is E, A, B, D, and C. So it's saying to complete this one that has a due date of 6 days and a processing time of 2 days first. Then this one of 9 days of due date of and 1 day of processing time. So that one is actually very low down there, which makes sense. So the next one would be the A, the 5-3. So we're making sure to turn that one in early, right? And then so we don't get credit for turning it in early, but we're not tardy in that instance. So EA, B, D, C. So EA, B, D, C, and that makes sense. And then so the one that we're leaving for last is essentially the one that like we're gonna be tardy on no matter what we do, right? Because it's got a due date of 3 days but a processing time of 4 days. So we like no matter what, we're like that project is gonna be tardy. So that makes sense as to why I would put that last. And then by iterating on that and iterating on essentially randomly iterating via this annealing process on all of the different possible outcomes of this, we can find out that it comes through the outcome here and then gets us the end result. But kind of the bottom line and the big thing to illustrate here is, again, that if we didn't introduce this chaos theory, which is essentially just the chaos theory that we're introducing within this particular algorithm, is that we're saying take the best solution, but then also there's a small chance that it will take the worst solution. And then it will throw that in there as well. And then over time, we want to decrease the probability or decrease the temperature of that worst solution getting picked and implemented into the output and the results. And then so we essentially like decrease that temperature and decrease that probability. And then by doing that, essentially the model understands very quickly then like, okay, like, and then it comes to the end result, like the most optimal result based off of that, and then essentially very quickly again. So it escapes this local optima problem that it gets stuck in up front, and then boom, finds the global optimization, and then it's just clean running from there. And then we wouldn't get this significant, like this steep drop off that we're looking at here, like that very steep line down to the global minima, if we didn't have the chaos theory within that, right? Like if we didn't have some sort of disruption, some sort of ability for the model to have randomness built into that. So that's what this all boils down to, right? Is the randomness is built into how this is working overall. And then when you're talking about LLM models or NLP or neural networks or any other part of AI, you're essentially scaling this up. Like you have this randomness built into the AI model, like into your LLM model, like times a million. Right? Like it's also has chaos theory algorithms that it's built on. It's also built on random libraries. There's a black box element behind it. These like I don't like to get into those elements overall because it promotes kind of like lazy thinking around um, LLM models and how that works overall. But so like there's always like the reason why those elements exist is because this is all built into the functioning of AI. And then if you remove that base level of the functioning of AI, it doesn't function as well overall. And then so uh, that's the overall equation that you have to deal with, and there's no way to eliminate that, right? Like that's just what the equation is. Like randomness equals good things happening uh, within AI and how it operates. It random through randomness, we can escape local minima problems and local optimization problems, and we can get to the global optima. And then so without it, we couldn't do that. So that's just how it works, right? It's very like black or white in that instance. And then so yeah, I'll leave this here. I think this is a good overall summation and introduction, basic introduction into kind of chaos theory, and then in this instance, looking at what we're looking at a simulated annealing algorithm. And then I'll make sure to leave the link to this particular Colab and notebook in the description. So if anyone wants to play around with it, feel free as well. Thank you very much.